So welcome to this lecture on VHDL as part of the course Digital System Design with PLDs and FPGA. Before continuing with the lecture, we will have a quick run through the last lectures portions. The last lecture we have completed the data types, basically the composite and the integer, real, scalar type, and then we looked at the concurrent statement with select statement. So a quick run through the slides. So let us go to the slide. So we talked about the data type integer, so what is predefined in the standard library and how to use it, and the real type which is probably less used, and a physical type, the time with the unit as femtosecond, and you can check what is the latest the VHDL standard kind of basic unit must be femtosecond only. So that is the various units specified, and we have, it is possible to define subtype on a type. The advantage of defining subtype is that you can use all the operators, unlike if you define your own data type, then you need to overload all the operators, functions which you need to use for this particular data type. And this shows various user defined data type enumerated. These are integer, this is real, and this one is a physical data type, and this is a subtype. And we have looked at the unconstrained array, and we said that standard logic array is defined as unconstrained, that is why we constrain it when we use it. And you can have multi-dimensional array, any number of dimensions, and we have seen an example of that. And you can have record, whereby you can kind of related signals or variables can be put together, and this shows some input output enable of tri-state gates are put together, and you can assign, like in as a record in structure in C, the similar syntax is used, and you can see that the component, individual component within is accessed with a dot. And if you have some signal, a part of it can be aliased, like we have used the top address line of a 32-bit address is aliased with the top AD. We have also seen various ways of assigning the rows. This is a positional kind of association, this is named association, this is like a string, and this one is again positional association with this others, hexadecimal base specification. And if you say others, means that everything is one value, that in this case it is 0, the other case it is tri-state. So this is very useful one, because if you have say a 32-bit bus which you want to kind of output, something is connected to 32-bit bus and you want to initialize it, or you want to tri-state it, you do not have to write, keep on writing Z and counting it 32 times and all that. You just say other Z, that is the most useful form of array assignment. And then we have looked at the important part, concurrent statement. As the name suggests, this is used in the concurrent body, that is in the architecture statement region. This cannot be used within a function or a procedure or a process, it has to be straight away used in the concurrent body or the architecture statement region. So the syntax of with select when is with some, you specify some input, you say select, for all mutually exclusive values of that signal you specify the output, the numerical values, or as a function of some other inputs. Okay. So we said that this is nothing but the truth table. In the simplest case, we have seen an AND gate, say A1 and A0, and for all the 00, 01, 10, 11, the value, the output is specified. It's a simple truth table. The equation is wherever there is 1, So that min term is the equation, or if you have multiple ones then you say or, if you have two ones then you say or and that choice. So you wherever one is there you pick up that min term or the next one and so on, and this we write when others for the simulator to completely specify all input combination, because standard logic can 2-bit standard logic can take 9 into 9 81 values and we are only specifying 4 of them. So Rust 77 is covered here. So you could even say 1 when others, but as I said specifying some known values will help you in debugging, like that if some of those kind of combination occurs then the 0 can happen. Even you can say tri-state, doesn't matter because it is useful for debugging and next we have seen the case where the output is specified for all the values of a input signal A as a function of B and C, okay, and that is a little more complex truth table. So you see when A is 0 0 then Y is B, so Y is 0 when B is 0, Y is 1 when B is 1 and so on, and the C's don't care. So this expands into multiple rows of the, each one is expanding into kind of 2 rows of the truth table, but when the equation is written it is kind of A1 bar and A0 bar and B, or like, so this is straight away this choice is A1 bar A0 bar and B is Y, or A1 bar A0 and B bar, and so each one is a min term or a product term or this or and so on it goes the equations. So that is what is shown here, and we have seen that the same thing, and one thing to remember is that whenever there is an event on A, B or C the simulator computes this, and as far as the synthesis tool is concerned it will look at the look at the description and form the equation that is simple as it is, and this can be used for example is shown with a multiplexer. So natural choice for the select signal is this, the select signal of multiplexer. So for various combinations 0 0 0 1 1 0 Y is A B C D like 0 1 2 3, and the equation is like this the select 1 bar and select 0 bar and A or and so on, okay. So each one is a min term or this one, and I am showing only YI, so because for a bus whether it is 4-bit or 8-bit the equations are same exactly similar for each bit of it, because it goes through the same type of AND or structure, and it is easy to confuse this kind of syntax with the multiplexers function, but we have seen that any combination circuit without priority can be easily specified by with select. So if you have multiple inputs, one output, then you pick up some input, and for all the mutually exclusive values of B you specify Y as some of A and C depending on your logic, and that is what is with selects provide you, and this is there is no priority, actually this is for all, it is a plain truth table with little abstraction. Maybe it will translate you are bringing A and C, so some more columns are added, some more rows come into picture. So it is still a kind of straightforward truth table, and as I said if you have the output has the same function or same values for different choices of the values, then you can use OR, and that is what this example say. So that is what is the with select concurrent statement. So let us look at the next one, which is when else, which is little more complex than the with select. So please have a look at this syntax. So which says that you have some output signal, it could be a single bit or multiple bit, it does not matter. You have an output signal which is assigned some expression, and this can be a numerical value like 00, 01 depending on the width, or it can be some input condition, input expression. You can say A and B or A bar or whatever, okay. When condition 1, that means condition is again an input, you can say C is equal to 3 or P greater than Q and so on. So some condition based on the input, then you say else, which was not there in the with select, okay, else some other expression when some other condition, okay, else and so on, okay. And at the end we say an else, which is, that means everything else is expression y, okay. So this naturally brings in the priority, okay. That means we are saying output is some expression when some condition, suppose we are saying a condition A equal to B, and we say suppose this is 2 bits and we say 00 when A equal to B, then we say else, it means that A is not equal to B, okay, and we say another condition, say D greater than B. So it means that the output is, maybe this was 00, this is 01, output is 01 when A is not equal to B and D is greater than 3, okay. When you say else, it means that it is not this condition and not this condition. That means you say A is not equal to B and D is less than or equal to 3, then maybe the output is expression 3 and some other condition, okay. So as you go down, the not of all the previous condition is coming into picture, okay. So it brings in priority. First thing to note that is that there is a priority. So it is a little more powerful because you see this condition 1 can be in terms of 2 signals, and when it comes to condition 2 it can be another signal, another group of signals, and this expression itself can be some inputs. So it is quite a powerful, quite an abstract statement, much more powerful than with select. It brings in priority, and most importantly the question is that is it are we completely specifying a truth table by this kind of structure or syntax, that is a question. You think about it, whether it's a truth table. The answer is yes, it is a truth table, but it is in a much more abstract, and I will show you soon, very quickly I will show you. This is nothing but a truth table. A complete truth table is specified in terms of all the inputs involved that we will see in a moment. So let us look at how the equations are derived for the combination circuit from this syntax. So again I am not putting down some signal, it is still little abstract. So you have an output signal and expression A when condition 1, else expression B when condition 2, else expression C when condition 3 and so on, okay. So the equation comes like this, output signal is expression A and condition 1. When I say and condition 1 is equal to working out the product terms, all the product terms of the condition 1. So it can expand into multiple product terms, okay. So it may be like you say D greater than C, there could be some product terms in terms of D and C or and so on, okay. So there could be multiple product terms. So it is still abstract, but then the meaning is that the equation is expression A and condition 1, or, and when you come here it is a not of condition 1. So expression B and not of condition 1 and of condition 2, okay. Or when you come here it is expression C and not of condition 1 and not of condition 2 and condition 3. So it brings, it expands like that, and if you remember your basic course, you would have seen a priority encoder. You will see there is an AND gate. As it goes down to lower priority from the higher priority, there is an AND gate with lot of bubbles becoming bigger and bigger. So that is similar thing is happening there, but there it is the single kind of normally the single bits which is going to the AND gate, not of the previous inputs and so on. So that's the same thing. So it's quite powerful. So let us see an example, and I want to illustrate how it is specifying the complete truth table. So let us take an example. Y is a single bit signal, A, B, C are single bit, like Y is output single bit, A, B, C are inputs which are also single bit, but these are inputs. P, Q, R are inputs and they are all 2 bits, so you have P1, P0, Q1, Q0, R1, R0 and so on. Okay. So you can imagine a truth table with P1, P0, Q1, Q0, R1, R0 and A, B, C and Y. Okay. So imagine wherever the values of P is greater than Q, irrespective of the conditions of R, A, B, C, so B and C, Y gets A, and when it comes other rows like P is less than or equal to Q, so wherever the rows in the truth table where P is less than or equal to Q, all conditions, all rows, and R is equal to 2, we write Y is B. Okay. Else for all other rows we write C. So it completely captures the truth table, but it's very powerful. I will show you the truth table. So I have put it, I have kind of compressed ABC. Ideally I should have put in the input section, this is the input section, this is output. I should have put A, B, C also, but to save space I have included A, B, C in the output expression, but it's easy to understand. Okay. So in reality the truth table is much bigger than this. So you look at this scenario where the P1, P0, Q1, Q0, R1, R0 are the inputs, Y is the output. So look at this scenario where P1, P0 is 0, 1, Q is 0, 0, R is don't care. So here P is greater than Q, so the output is Y is A. As I said, you should have an A column, then if A is 0, Y is 0, A is 1, Y is 1. So it's simple, you can derive that. And when it comes to this case, you see P is 0, 1 and Q is 1, 0, so the P is less than Q. Then R, you look at the value R, 1, 0, this is 2, then as specified the Y is B. But in other cases where P is less than Q and R is kind of not equal to 2, the Y is C, and you can populate these values all the way from 0, 0, 0, 0, 0, 1 all the way, that all the way it comes to 1, 1, and 1, 1 you see is P is not greater than Q, R is not equal to 2, so this is C. So this is at least this truth table has a 6 columns, so it is kind of 64 rows, but if you bring in ABC then it is 6 plus 3 9 kind of columns. So you will have 512 rows for this truth table, but you see the power of this statement, all that 512 rows are compressed into 3 statements, and many a times this is how we think. We don't think like though when you have a spec of a combination circuit you write the truth table, but we always think in terms of abstract like this. You have some inputs, then the problem statement itself could be like this. You have P is greater than Q, then the output is this, otherwise if some other input is equal to something then the output is this, if none of this is then the output is something else and so on. So that also shows that the language allows you to think real life, but you should not lose sight, you should not think that this is some magic. ultimately this we are specifying the truth table, and a word when a simulator, as far as simulator is concerned, if there is any event on P, Q, R, A, B or C, this Y will be computed, or this you can imagine like a process with this A, B, C, P, Q, R in the sensitivity list. Any event happens on any of these input, Y will be computed, and Y is, if there is another statement which is concurrent, then that also will be computed. But as far as synthesis tool is concerned, say it is going to look at say P greater than Q and there is an operator greater, so it goes to library, pick up the greater operator, and that would have been written as already as a synthesizable code which shows the structure of greater than Q, like some input greater than some other input. So that will be replaced, the synthesis tool will plug in that circuit here, and if you think this could be a kind of when a kind of multiplexer, when this condition happens, this output is this input is led to the output. If not and this condition happens, this input is led to the output. So this will be some kind of various operators, implementation of operators, some kind of priority and some kind of muxing happens ultimately as far as synthesis tool is concerned. So we will see how the synthesis tool does this as we go along. I am giving you a kind of taste of how things happen now only at the beginning. So this just I have written the description in this code, wherever there is P greater than Q, where there the Y is A, when it comes here whenever there is P is less than or equal to Q and R is 2, that is B, and for all other conditions it's C, and any event happens on any of these input, the simulator computes, synthesis tool looks at the operator and infer the operator and replace it with the template structure from the library. That is what is happening. So let us take an example which is a priority encoder. So you can imagine I have not drawn the picture, but then you can imagine there is a block where there are 3 inputs A, B, C single bit input, which is encoded into 2 bit because we have 3 bits, and so where the maximum priority is given to A, next priority is B, next priority is C, and none of that happens, the output shows 1 1. So the coding is that the prior, which is the output, is 0 0 when A is equal to 1, else that means A is not 1, A is 0, then and B is 1, then the output is 0 1, and when it comes here A is 0, B is 0 and C is 1, then the output is 1 0, and when it comes here none of this is 1 or A is 0, B is 0, C is 0, then the priority output is 1 1. So this shows a natural very simple example of using the when else. Maybe we will see a little more kind of little more complex example with the when else. So let us look at this example. This bring in kind of 1 or 2 elements we have studied together, the array assignment, the in out mode and when else, everything is put together so that you get a taste of somewhat real life coding. So just please look at this structure. It is a bidirectional buffer or a transceiver, so please look at it. So a bidirectional buffer gives the connects 2 lines in either direction. So you see here when the direction is 1 and enable is 1, A is driving the B. So you can imagine this as some output section driving a bus or something like that. This is where everybody is tied together, similar structures. So when direction is 1, enable is 1, this is enable, and since direction is inverted here, so this is disabled, this is cut off, this output is cut off though the input is coming here. So naturally A goes to B, and when opposite is the case, when direction is 0, this is cut off because this is gets 0 and the enable is 1, then this is enable, so this part is cut off, and B, assume that B somebody is driving, some output is driving this, and B goes to A. So mind you, this is bidirectional, you can drive it and somebody else from outside also can drive it. So this has to be the mode of this B is in out, mode of A is in out, because in principle when this is cut off somebody can drive it and so on. So this is the library description of the VHDL. This is a standard logic 1164, and this is entity transceiver. Trans is port, we have 2 signal and which are 8 bit, okay I am showing 8 bit because the control signals are common for all the tri-state gate. So AB is in out because of this structure, standard logic vector 7 down to 0, enable direction is in standard logic and transceiver, and we define the architecture as some name of this entity is begin, and end this architecture names ends this part, and this is where we write the concurrent statement. Now you see we are going to write this path first and this path, because in the concurrent statement mind you need to have a statement for one output and another one output. So we are going to write B output first and then A output second. So that is what we are doing. B is an output, B gets A when direction is 1 and enable is 1, else it is tri-stated. So we say, and this is being a bus, we say others, the assigned Z, that is it, okay. So which says that B gets A when both are 1, else it is tri-stated. Similarly we define the output A, so A gets B when direction is 0 and enable is 1, else it is tri-stated, this is tri-stated, else others is Z, ND flow. So this shows how to use the when else in a more practical, more real life case. We have seen how the in out is used, we have seen this array assignment, the others close here. So that shows an example of using when else, another example of using when else. So let us look at the, so we have completed the concurrent statement. The concurrent statement is essentially 2 types, with select and when else. We have some loops, we will see that together for both the concurrent and the sequential together, and the main concurrent statement are with select and when else. With select is no priority, output is normally specified as for all the values of some input. The output can be specified as a simple truth table of numerical values, or if you have other inputs you can write as a function of those inputs. In that case it translates into multiple rows of truth table, and we have seen some example of with select coding. The next little more abstract one is when else, which is little more powerful. We can specify priority, we can specify condition in terms of multiple input, the expression can be some other input, so it can capture much more real life scenarios from the specification given for a combination circuit, and we have seen how some simple 3 kind of choices can translate into a huge truth table. So that is a power of when else, and we have seen the coding for a priority encoder, and we have seen the VHDL coding for a simple bidirectional buffer or a transceiver with 2 controls, enable and direct. So let us now move on to the sequential statement, which are more useful, more complex than the concurrent statement like with select and when else. So let us move on to the sequential statement. There are two types. This is identical to what you have learned in a C language or sequential languages. So you have if then else and case when. Only thing is that it is now kind of related to the hardware. We are describing the hardware. So all the equations are different, it's not you should know what is the hardware behind it. When you use this statement you should know what hardware it means, okay. It is not mere kind of some variables you are working in a sequential language, okay. That should be kept in mind, and I will tell you what is the kind of equations, Boolean equations or the hardware you get when you use this syntax. So the simplest syntax is like this: if some condition 1 then some output get some expression of the input, okay, or numerical value, it does not matter. So if condition 1 condition in terms of the inputs, then y gets a, else. So the priority is there, else means if not of this condition then y gets b, okay. So end if, so a and b are input signal, the whatever signals in the conditions are inputs. So the equation is y is a and condition 1, or the moment you say else, or b and not condition 1. So which is exactly similar to the when else, okay. So this one is exactly similar to when else, but mind you the sequential statement can be used only in the sequential bodies like process, functions and procedure. You cannot write if or case directly in the architecture statement region of the VHDL code. That is not that's not possible. So you should always use sequential statement in process, functions and procedure. So let us look at more complex kind of syntax. So basically the conditions like in when else, it is general conditions, you can say p greater than q, c equal to 3 and things like that, and there is priority. So the next kind of complex syntax is if condition 1 then y gets a, instead of else you can say else if. It is not ELS EIF, it is ELS IF. Else if condition 2 then y get b, else if condition 3 then y get c. At the end you say else, which comprises of all, not of all the conditions. So you need to have, when you specify the proper combination circuit, you should have the last else. I will tell you what happens if not there. So it is very important which comprises of everything else, then only the truth table is complete, okay. Because we are putting the condition which means some rows of the truth table. When you say last else, all other rows in the truth table, that is what it means. And you can see that the equation goes like this: y gets a and condition 1, or b and not of condition 1 and condition 2, or c and condition 3 not of condition 2 not of condition 1. So exactly like when else it builds up, as I go down, when you come to the last one which is d and not of condition 3, not of condition 2 and not of condition 1. So it is like a priority encoder, it builds up, and this itself can be very complex. We are kind of abstract. Condition 1 can be translated to multiple rows of the truth table, a lot of min terms or product terms it can come depending on the condition you put. So that is if then else statement, okay. Now I said it is equivalent to when else, but so the question is if it is just equivalent to when else, what is the big deal, why you have to write a process and put this inside the process. So can you kind of think of a reason how if then is different from when else. So you look at the when else, the when else statement was earlier, say here this is the when else. an output is specified as some condition exactly like if then. So what could be the difference between when else and if then? Think for a while. So you can think of the C language that might give you a clue. So basically if you look at it, what it allows is that when you say condition 1, you could write another input, you could write Z gets something, Z gets something, Z gets something. So in an if then else structure you can specify multiple outputs, okay. That is one difference between when else and if then, and that is very useful, very powerful. And so that is one, you can specify multiple output. And another thing again, if you compare with the kind of sequential language like C, you can write in principle, say here if condition 1, then I can nest it, I can say another if, you can say if condition say 5 under this condition, then Y gets A, else Y gets something else, and you say end if, okay. So you can nest if, okay, everywhere, you can have an if here, if here, if here, and so on, okay. And it's not that you can go on nesting it, many synthesis tools limit the level of nesting because the equation can become messy and you are bound to make mistakes and so on. So if then is else is equivalent to the when else, but it support multiple output, it support nesting, that is very powerful. You can bring in a lot of complexity in description by these two, the multiple outputs and nesting. So this is what I am going to show. So you have say Y and Z output and 3 inputs A, B, C, all are let's say multi-bit, and now you can write say if condition 1, then Y gets A, Z gets A and B, else if condition 2, Y gets B, Z gets C, else if condition 3, then Y gets C, Z gets A, else Y gets D, Z gets B, and so on. So this shows you that you can specify multiple output using this same if, and the equations are similar, you know how to work out the equation, there is no great complexity as far as the equation is concerned. You have the same inputs in condition as column, ABC as columns, then you have a Y output, Z output, you can write work out the equation, say Y is A and condition 1 and B and not of condition 1 and of condition 2. When it comes to Z is A and B and condition 1 and or C and not condition 1 and condition 2 and so on, okay. So that can be worked out, but if you are clever you should be asking a question, say all fine, it's great, but this assumes one thing, that the condition for these outputs are all same, okay. Maybe that you cannot the relation between the input and output are such a way that you have no way to specify like this, Z is A and B not on this particular condition, little more restrictive, under this condition some more conditions are required for A and B, then you are in soup, you cannot use this kind of structure, but that is where the nesting helps you. You could write say if condition 1 Y gets A, then you can write if some other condition is met then Z gets A and B, else something else. So you could further nest if to specify very specific conditions you require for multiple outputs. So that is where the nesting is important. So you can have a more complex behavior or structures can be specified by nesting. Suppose we will not be like in the case of multiple output, we will not have the same conditions satisfying all the outputs. So you could have like this, if condition 1 then maybe Z is written here something, then you say if condition 2 then Y gets A, else if Y gets B, end if then else if condition 3 or 4, then so on. So you could nest if, and the equation as far as y is concerned, it comes like this: y is a and condition 1 and condition 2, because it is under this condition 1 we are putting, or then you say b and not of condition 2 and condition 1. And when it comes to this else if condition 3 for say z or something like that, then this condition 2 doesn't appear there, and so you can work out. So this is where the nesting is useful. And let us come to another point. Okay, what happens if you miss else in a if case, like you write if condition 1 then y gets a, and we don't write else, we just say end if. And mind you, this is a kind of valid VHDL syntax. VHDL support this, the simulator support this, synthesis tool support this. So what is the meaning of this? So you can attribute different meanings to it. You can say if condition 1 is not met, y can be 0, y can be 1, but these are less probable from the description. But what is the VHDL attributes or VHDL take this for is shown here. Okay, it is just by definition, don't kind of argue on why this should be like that, but this could be the probable meaning, and the VHDL take this in this way. Like it means if you write, if you miss else, it means that if this condition is met then y gets a, else y is y itself. Okay, and that is funny, that is dangerous. Okay, in the sense that it shows a feedback. Okay, if this condition is met, some y gets an input. If this condition is not met, the output is fed back into the input. That's the meaning of it, and I am showing and so there is a memory, it memorizes. If for this condition it is normal, input goes to output. If this condition is not met, it memorizes the previous one. So it is called implied memory, because this code implies a memory, or inferred latch, or you can say this code infer a latch from the written code. So that's why it is called implied memory or inferred latch. So the situation is like this: if y and a are single bits and there is a condition, maybe p greater than q or whatever, so that is the decode of this p greater than q. When that is 1, a goes to the y, and if y is if that condition is not met, then this path is enabled and the y is fed back and it is latched. Okay, and this is nothing but a 2-to-1 mux. So this you can replace by a 2-to-1 mux with the select line, and the select line is the condition 1. When the select line is 1, a goes to b, otherwise the b is fed back. So this you can replace with the 2-to-1 mux, and with an inverter you get a latch. That's a normal latch kind of RTL symbol. So that is what you get. Okay, so this is very valid, and when if you need a latch like this, you can write a code like that. But the question is that can we have a latch in the concurrent statement? Okay, concurrent statement like with select and when else. The answer is yes, because we, at least in the case of when else, because it is equivalent to if then. You can imagine, you say when, you say output is something when some condition is met, and you say, instead of saying else, you keep quiet, you don't state that, then you get a implied memory or inferred latch in a concurrent statement. So, or in the with select case, you specify a condition, a decode, and you don't specify anything else, then you get a latch. So let us look at the syntax. So with, suppose you take with, it say this is the enable of the latch with enable select y gets A when 1, and we are not saying something for when 0 or when others. Okay, you say just say y is A when 1 and we don't say what happens when others, that means y gets y when others. Okay, that is the meaning of it. Or you can even say like this, with enable select y gets A when 1 unaffected when others, that means the output is unaffected when for the other cases, both are same. Similarly for when else, y gets A when enable 1, we don't say else, then you get the same thing, or you say y gets A when enable is 1 else unaffected. Okay. So for concurrent there is a syntax called unaffected, so it means that it retains the same output, that is the meaning of it. Even for sequential statement there is a thing called null which will give you the same effect. That means that here you can say, instead of this you can say if condition 1 then y gets A else y gets null, means y will remember the previous output, that is the previous value, that is the meaning of it. So you could specify in principle null. So that is how you write inferred latch or implied memory using the concurrent statements. Okay, and unaffected and null can be used. And now mind you, wherever you don't assign some output, you don't write unaffected and null, you will get a latch. Okay, so be very careful, null doesn't mean initializing it to 0 or something like that. So don't write null wherever you feel that something should be initialized to 0. Null will give you a latch, and don't write it unless you require it. Okay. So let us see the use of this, and you are not, normally we use flip flops for as memory in the serious design, you don't use a combinational kind of latch in real life, so we don't use it. Okay, so what is the use of this kind of implied latch? So the first thing is that the implied latch or implied memory or inferred latch is useful in specifying the behavior of latches and flip flops or registers. So we are discussing the combination circuit now. So we are discussing how the combination circuit can be described using the concurrent statement and sequential statement. We have not yet gone to the sequential statement, we are still discussing the combination circuit, but when we go there we will see how this description helps in specifying the memory for memory part of the latches and flip flops. But in real life when you write combination circuit, unintentional implied latches can happen. Okay, so that doesn't mean that you will write code like this, but when you have complex code, when you have a lot of multiple, say one scenario is that we take this example and where multiple outputs are specified. Say here suppose you have y, z and maybe u is specified everywhere, and you cut and paste, you copy paste, that is the usual the scenario nowadays, a lot of copy paste happens, and suppose by mistake you forgot to mention z here. Okay, you copy pasted and you forgot to mention z here, that means it essentially means z is z as far as condition 3 is concerned. So when it comes to this choice, that means condition 3 not of condition 2 and not of condition 1, z will be fed back to itself and you get a latch. And all the more, not only in multiple output, when you have multiple nesting, very complex nesting which is unbalanced, like you have an if and under that in various choices of if, some has another if, some doesn't have if, and there are multiple outputs, it can be very complex and you can really miss some output to specify, because it is little difficult to work out all the outputs properly. In such cases you can miss some output and you will get an implied latch, and it is extremely dangerous. I tell you, and this is one of the as far as I am concerned, what I have seen is this is very common error an inexperienced designer commit in VHDL coding, that is this implied latch when not in simple case, because in simple case it is very evident when you have multiple outputs and when you have nesting, very kind of complex nesting in the sense that is unbalanced, then you are bound to make mistake. Some output is not going to be specified properly for some condition and you will get a latch, and mind you it is very difficult to debug that, and because when you make a mistake and you look at the code, very less likely that you will kind of unearth that bug from the code, because you are very sure, everybody is confident nowadays, and you look at the code 10 times 100 times you will not discover that error. And if you simulate, mind you will never 99.99% you will not be able to unearth such an error by debugging in simulation. I will tell you in a moment what is the reason why it will not happen, and if you are giving it in a real life, if you are in a design team, many a times the verification is done by some other poor soul, and he would have worked out a lot of test vectors for verifying the functionality. Even there it cannot be unearthed. So in a moment we will see why this is difficult to kind of debug. The first thing is that it is not enough if you verify all the condition, like you have some inputs and you like suppose you have 4 inputs, 4 single bit inputs, so you have 16 condition, or you have say you have 1024 input test vectors, you run it through, or even you have a 1 million test vectors, you run it very systematically 1 million test vectors, still this error won't be brought up. Why it is so is because suppose in our coding you miss one output in condition 3, okay. Now you have, as I said, you have simulated the million condition, all the possible condition, but before the condition 3 you have suppose simulated the condition 2, for which this missing output had the same value. Say you are expecting in condition 3 some value, suppose the test vector you have simulated for condition 3, the one before you simulated is condition 2, and suppose the condition 2 and condition 3 has the same output as far as this particular one is concerned, then the output will be correct, absolutely correct. So to unearth this error you have to work out a condition where the output is different than this particular condition, and if as a designer you inadvertently made a mistake, you are very, because that is by mistake you missed that and you have not realized this, and you will not be able to make that condition to unearth this error. So the best thing is not to make some mistake, make this mistake. So it is in real life also it is better, some mistakes are better you don't make such a mistake, like you drive on the wrong side of the road and then you are bound to crash into somebody else in a two-way road. So like it is better you don't make such a mistake, you be very careful that you don't miss output, and be very careful when you nest the if, so that the implied latch or implied memory or inferred latch doesn't occur. So I think that is where the next statement we are going to look at is the case when, and what we have left is the loops, but maybe that we are coming to the end of the lecture. We will look at it in the next lecture. So quickly we can run through the if then. If then is identical to the case when else in the concurrent statement. So simple condition is if condition 1 then output gets something else, output gets something else. The equation is similar to when else. The complex condition is you keep on giving various conditions, at the end you say else for all, not of all the conditions. equations are similar to when else. The power comes from multiple outputs and nesting, and you could specify multiple output. When the conditions are not identical, you can start nesting. You can think of nesting in various ways, and when you say if, you write if under and if, it translates to the condition 1 and condition 2, and when you come here condition 1 and not of condition 2 and so on. So you can kind of work it out, and when you don't specify the else you get an implied latch, and which is a latch which is useful, and you can use concurrent statement to get the same effect, and you can it's useful in specifying memory in the case of flip flops and latches, but in the combination case when you have multiple output, the nested if, then unintentional latches can happen, and as I explained it is very difficult to unearth in simulation because you made it by mistake. To work out the condition is quite tough, and there's no point in, there are people who make a mistake which can be corrected in 5 minutes, and next 1 week you will simulate to unearth that error. It's not worthwhile. You plan properly, you code properly, you go through the code, you take any number of spend as much as time on paper thinking about it and design, then less verification will be there. An experienced designer or experienced engineer should plan properly, go systematically, so that with minimum iterations things work properly. That is how you should work out things, than rush through the things arbitrarily, quickly writing, cooking up something and forever debugging, forever sorting out the problem. What one mistake you made in 2 minutes can kill your 2 weeks of time, many people's time. So don't do that, plan properly. So that I stop here today with this when else and if then else, which are kind of similar, but if then is complex, more useful. So next class we will take the case when and the loops. So please revise it, write some examples of your own using these statements. So thank you, I wish you all the best.